Hello YouTube, RJ. We're going to continue on building modules so that we can build our HF radio. And today we're going to talk about mixer, but not really. We're going to talk about the module we're going to build, but then we're going to talk about and design a testing device to help us build it. While we're looking at building a mixer, in this case, the schematic you see here is a typical standard diode ring mixer, double balanced diode ring mixer. And very important part of your radio is, of course, your mixer and your modulator, demodulator, which is just a mixer used in a different way. We're going to start out with this basic mixer design, and then we're probably going to tweak it and try to get a little better performance out of it. We'll probably start with it, and once we get a working radio, we probably will add on and play with it, test, and try to improve upon it. But right now, the reason we're talking about our diode mixer is the first thing you need to build a diode mixer is matched diodes. We've got to get diodes that match. Each diode, as with all semiconductors, varies. And in the case of a diode, we're concerned about the forward voltage, the voltage at which the diode will turn on. If these vary in a ring mixer, you'll have different parts of the waveform turning on at different times, and you'll get some ugliness going on we don't want. Why do we have to match these things, and how do we do it? Well, let's look at this chart here. This is a diode. I don't remember the model diode, but it was the one I could find that had this chart. It's called the scattering limit. And what this chart is telling us from the manufacturer right out of the data sheet is two different things. One, at different currents, the forward voltage where it turns on will vary. The higher the current through it, the higher the voltage at which it turns on. We can see this by the curve of these curves. But the other thing it shows us is that we have two curves. Now, why do we have two curves? Does it turn on at two different voltages? Well, no. Some of them can be as low as this curve. Some of the same diodes from the same manufacturer in the same package could be as high as this curve. This is the scattering limit. This is how much difference you have to expect that your diode will have. In other words, you pull a diode out of the bag, they're saying, we promise you at 10 milliamps, your voltage forward will be somewhere between here and here. We don't know exactly, but we know it'll be between here and here, and you need to plan for that. So this is what gets us in trouble, is when these are turning, if you put diodes in a ring and they're turning on at slightly different voltages, it affects your quality. The other thing I want you to note out of this, so really there's the three things, is that as we go up in current, notice the scattering limit gets wider. If we go up to 100 milliamps, it's quite wide. And you continue on towards an amp, and man, it really gets wide. Oh, here's the diodes, 1N914. And of course, it can handle a lot more current than the diodes we're going to be using. I couldn't find this chart for the diodes we will be using, but you can see as you go up in current, diodes variations get wider and wider. So for this reason, we have to do a very important thing when we're testing diodes. We have to set a fixed current, whatever you're going to use. I typically, for ring diodes, I'm going to use 10 milliamps instead of 1 milliamp. 1 milliamp gets really tight, so you're not going to see much. You're going to end up with diodes that you can only do such a good job of separating. As you go up in current, that they're going to show themselves to be more and more different, and so therefore you can get a better idea and classify them closer together. I hope this makes sense. Think about it this way. If we went up to 1 amp, wow, look at how much difference those same diodes would show me. So it'd be easy to see the differences between each one of them. So down here, it'd be a little harder because there's not going to be much difference between them. So as we go up in current, this gets wider. Now, could we use an amp? Well, not on the diodes that we're going to be using. They won't handle that. 10 milliamp is a nice, safe amount, and it happens to be the upper range of what they may be used as a ring diode. So I tend to target 10 milliamps. What we need is to be able to supply a fixed amount of current to a diode, no matter what its voltage is. Now think, Ohm's law kicks in. If the voltage is varying in most circuits, that would change the current. Because of that, we can't just put like a resistor to limit current and feed to a diode, because each diode would vary and make the current go up and down, and you wouldn't get an accurate reading. So what we need is a constant current source, something that will provide a certain amount of current no matter how many volts it takes to drive the circuit. That's what we're going to do. And so the next thing I'm going to bring up is the circuit I put together to do this. And here's the LT Spice version of a test circuit I put together. And what we're using is an LM317 voltage regulator set up in, this is a very standard circuit. You're going to see it often. It's right out of, in fact, you find it in the data sheet of the LM317. It's a constant current source using an LM317. And then you see these two resistors here. They're going to set the current. This is a actual fixed resistor. This is a potentiometer. So what you're going to have is a potentiometer here that allows you to adjust your current to where you want it. And then this circuit is going to apply a fixed current across these points, whatever you set it to. Now you say, well, okay, why is this resistor in here? Well, the problem with having the pot on here is you can turn the pot all the way to 0 volts. That means that you can drive the current of this unit way up there. And we don't want to do that. First of all, it's going to get hot. 2, your diodes probably can't handle the kind of current it's going to deliver temporarily. So this is kind of a limiting resistor. This makes sure we don't get out of control too far. And then this one, that way when you're at 0, you're still limited on current somewhat. Then as you adjust the pot, you adjust the current between this point and as close to 0, which in the case of the LM317 is about 1.2 roughly milliamps. So you can get down to about 1.2. In our case, I think I've got it set up to get us up to, oh, we'll have to look when I get back on the bench, but I think it's about 50 milliamps. That current comes out. This is your feedback to your regulator on your adjustment pin that makes this current stay steady. It puts out a fixed amount, and what it does is it monitors it and constantly adjusts to make sure it keeps the voltage at a certain point, in which case the current is the same. So it comes out, and then we put a diode across here to test. This is our DUT, or device under test. And over here what we have is just a little bit of filtering, not really that necessary on a battery, but I like to play it safe to keep oscillations from happening in your voltage regulators. 9-volt battery will supply this device. It'll be a self-contained device. It'll put the current across here, and of course then we could put a voltmeter right here and here and see what the drop across here to know what the forward voltage is of this diode. Then we can test 10 of them and we can categorize them and separate them. You say, okay, well, RJ, what the heck? Why do you have all this hanging off of it? Well, I decided to make mine really self-contained. I didn't want to have to use a separate meter just because I had something in the drawer I could use. Thought it would be neat. I have a little milliamp and voltage meter that's going in the device that we're building. And the problem that I ran into with it is, while it's great for milliamps and it works perfect for that point, allows me to adjust my current and monitor at all times, I can't look at millivolts. I can only look at 10 millivolts, and that just wasn't accurate enough for me. To get around that, so that I could use this inexpensive meter I have, what I did is I went ahead and put an inexpensive LM358 op amp in here and set it up as a 10 gain non-inverting amplifier across here. And what that does, it allows me to take the output and feed into the meter, and now everything's multiplied by 10. So instead of 0.6 volts reading 0.6, it reads 6 point. So now I've gained that 1 millivolt. Everything is times 10. So if it read 6.21, it's actually not 6.21, it's 0.621. You just move the decimal point over, and that allows you to separate very fine separations of the diodes. So it's just a workaround. It's just a lazy workaround to allow me to use a very inexpensive little, AliExpress, Amazon type meter to pop in there. And you'll see this as we go forward. So anyway, here's my divider resistors, okay, to set my gain. Well, we all know these resistors are not going to be exact. Even if you went with 1% resistors, they're not going to be exact, and that's going to lead to a little bit of error creep. So what I did was, this circuit, I actually installed this as a multi-turn variable trimmer instead of a fixed resistor, and that allows us to calibrate this once we're done and get it to be exactly 10 times the reading. And it's a very simple one-time calibration. When you assemble it, works great, and then you're good to go. We'll see that as we move along. So once I laid this out, I went ahead and I built this in prototype style. Let's jump over to the bench. We'll build this, and then I will show you how it works. Okay, let's see how this thing works now that we've got it put together. Let's see if anything blows up when I plug it in. Let the smoke out. No, doesn't look like it. Now, looks like we can see the digits okay. And what you're seeing is you're seeing that we are, let me adjust this knob. This is our potentiometer. Now this is a multi-turn because I've had experience with these types of circuits in the past where I know it's very difficult to tune them accurately with a small 270 degree potentiometer. You're looking at your milliamps at the bottom of the screen here, and you're looking at your voltage that's being measured at the top. So if we take this to 10 milliamps, as so, okay, this diode that's plugged into the board right here is reading 7.47, which we know is 10 times the voltage, right? So it's really 0.747, but that gives us all the way down to our 1 millivolt, which is what I was looking for. That's where the op amp comes in. Now, what I didn't show off camera, what I didn't show is this trimmer right here. I hooked up my meter, and what I did was I applied, I put a short across here and set my current, then put the diode in to make sure that my current stayed the same so that my constant voltage or constant current source was working correctly. It was. And then what I did was I applied a voltage directly, pulled the diode out, applied a voltage from my power supply, and gave me an accurate voltage. And then what I did is I set it up to say, I think I did 0.8 volts. Yeah, I think it was 0.8 volts. And then what I did was this voltage was slightly off, so I adjusted this trimmer until I got exactly 8.00, thereby calibrating my 10 times gain. Then I turned around and did tests by adjusting my power supply in different voltages to see if it stayed 10 times, and it precisely did. So once you do this one-time calibration, you're done. This will be 10 times, so it simply fools the meter into thinking it's looking at 10 times the voltage and allows us to get down to 1 millivolt. So that's the circuit, and as you can see, it works well. 9-volt battery, easy to adjust. No problem adjusting whatever milli. So let's take a look at something. Let's go back to 10. Remember our charts showed us that diodes' forward voltages were affected by the current through them. So here we are at 7.545, or other words, 0.745 volts. Watch as I turn the current down. Watch how much the voltage changes, okay? Now you can see that if the current's bouncing all over, we'd never be able to categorize these diodes. You got to have a very precise current to compare the forward voltage, and that's why we need that. So this is working very, very well. So now I'm ready to build a circuit board for it. So I'm going to go over to the computer. I'm going to take this design and I'm going to jump into DipTrace and I'm going to design a circuit board for it. So we'll pick up over there at the computer to do that. Okay, you can see I've already designed the board. I wasn't going to make you guys watch me do the whole project. I've done it in other videos if you want to see that. Here's the board. You can see the layout's pretty straightforward. Not a very big board at all. Down near the bottom here, I've got the two big rings you see, cathode and anode. These are for the posts that are going to come through the box and actually allow you to connect the diode. The board will literally connect directly to this board and actually be supported. That's the mount. Here's the current meter, the lines from the meter hooked to current, and then these are the three lines that run power, ground, and the voltage sense into the meter. We've got our LM358 here. This is the trim pot for trimming the ratio on the voltage to get the op amp for 10 times. 1K pot here, that's the big pot, the big potentiometer you'll turn to adjust your current to what you want. Here's your LM317. Here's the switch. What's going to happen is you're going to have the battery, 9-volt battery and ground come in here, and it runs through a set of connectors for a switch, a toggle switch to turn it on and off. Feeds power to everything. When it's on, turns everything off so the battery don't go dead. Now let's see, what are we missing? This is the 22 ohm fixed resistor that goes in parallel, or I'm sorry, in series with the 1K pot to limit the current. And that's pretty well it, except for down here you've got, as I said, the cathode and anode to make sure we know which way we're hooking up the diode stuff up on the post, which post is which. And that's the design. Well, there's also the capacitor here, just a little bit of capacitance for the LM358, and that finishes it up. And so at this point, the big thing is we're going to, this will be it. I'll send this out, have this board made. I'm going to end the video here because it'll get too long, and then when the board comes back in, we'll have the next video where we actually assemble this board, do the case, do the silk screening, finish up the project, test it all out, see what we think of it. So see you then. Thanks for watching.